This is going to be our last lesson on kinetics, and hopefully with what we do today, it's going to tie a lot of concepts that we've already discussed together. We're really going to focus on the details of molecular collisions today. We're going to introduce the collision theory, which will help you better understand why certain factors affect the rates of chemical reactions. And then we're going to look at reaction mechanisms. This will be all very new to you. It is pretty easy, provided that you practice enough, and you'll have a lot of practice today. We're also going to look at some AP Part 2 questions, so that will really help you get ready for your quiz. All right, and we'll be doing a lab on kinetics at the end of the week. So your big idea 4 is indicated here, and we are going to pick up with the collision theory. We talked about integrated rate laws last time, and your do now showed that some of you recall how to read those different graphs. Make sure you master that. With theories of chemical reactions, or chemical kinetics, the first theory we're going to talk about is the collision theory. And this helps to explain why increases in temperature, concentration, and surface area typically increase reaction rate. Reaction rate is proportional to the product of the frequency of molecular collisions, so how often they happen, and the fraction of those collisions that are successful or effective. And when you're thinking about effective collisions, 2 criteria must be met. The particles must have enough force to overcome the activation energy. Activation energy is the minimum amount of energy that must be overcome for reactants to be converted to products. We'll be looking at activation energy. We can see it. I've got slides from 2 different books here. This is from an older one, but I like this one, and we're going to take a look at this. Let me show you activation energy just for a minute. Right here is a reaction profile. This reaction is actually exothermic. When product energy is less than that of reactant energy, the reaction is exothermic. Exo as in exiting, releasing energy. So this value here would be less than that, and you subtract products minus reactants, so you'd get negative exothermic. The activation energy is the minimum amount of energy that must be overcome for a reaction to occur. So here's potential energy on the y-axis, typically in kilojoules. Reaction coordinate or reaction pathway, this shows the progress of the reaction from reactants to products. So here's the energy of the reactants, here's the energy of the products. When product energy is less than that of reactants, the reaction is exothermic. Should be able to distinguish between exo and endo, but we'll also talk more about that in thermodynamics a little later on in the year. Activation energy is EA, and this is the energy from reactants to the tippy top. So you can think of trying to roll a ball up and over the hill. You can push it, it may come back down. You can push it, it may come back down. At the highest point of the hill, it will either come back or it will go over. And the activation energy is the combined kinetic energy that colliding particles must have for the reaction to occur. So with the collision theory, particles must hit each other hard enough, that is with enough force, to overcome that activation energy barrier. The particles also must be oriented properly, so they have to have the correct orientation. For example, oh, where is it? Disappeared on me. Get back here. There it is. For example, if we look at the decomposition of NO2Cl to nitrogen dioxide and chlorine gas, What you're seeing in the top panel is an unsuccessful collision. In an unsuccessful collision, you don't get product formation. So these two particles can hit one another hard, but if the particles are not oriented properly, you'll get no reaction. We want to generate chlorine gas. In order to generate chlorine gas, the chlorine atoms must collide in the proper orientation. So if we rotate this molecule 120 degrees, the chlorine atom will be here. Now the two can hit one another hard enough to overcome that activation energy barrier, and the chlorine atoms are oriented properly, well, the two molecules are oriented properly such that the chlorine atoms hit one another, a bond will form between them, this bond will start to break, and now you're going to have a successful collision. Two factors. Toward the end of the class, I'll show you an AP question from a practice exam. It's a part 2 question, and they ask about these two factors. So the particles must hit each other hard enough to overcome the activation energy barrier. That last piece is important. And the molecules must be oriented properly. Same thing that you see if you watched the Yankee game last night, several home runs. They went through this whole analysis about why the Yankees weren't hitting. They were swinging hard, they were swinging hard, they were swinging hard. So force was definitely there, but no orientation. Bat wasn't making contact with ball properly, ball not going anywhere. And if you watch the whole analysis, they got into it. And actually, he was dead on the money. Never liked the Boston Red Sox guy so much. He was smart. Anyway, proper orientation, enough force to overcome the activation energy barrier. Same thing with concussions on the field. Last year, 3 kids had concussions. You got to get hit hard, and you got to get hit in the head, right? Or your head has to make contact with the ground. So you're looking at enough force to overcome the activation energy barrier and proper orientation. Remember those factors. They sometimes come up, and this could be the year. Successful collision, unsuccessful collision due to the improper orientation of the molecules. Critical. Any factor that increases the likelihood of an effective collision will increase reaction rate. And make sure you can explain that in regard to the factors. So for example, when you increase temperature, particles move faster. When they move faster, they're more likely to hit one another hard enough to overcome that activation energy barrier, increase in reaction rate. When you increase the surface area, you have more spots on that molecule with which to collide effectively. Anything that increases the likelihood of an effective collision will increase reaction rate. Same thing with concentration. As you introduce more and more reactant, the likelihood of an effective collision increases. Any factor that increases the likelihood of an effective collision will increase reaction rate. A catalyst is a substance that also affects reaction rate. A catalyst is a substance that's not altered or consumed in the reaction, but it typically positions molecules so that they can collide properly in the correct orientation. So any factor that increases the likelihood of an effective collision will increase reaction rate. Make sure you understand both pieces here. And we'll come back to the temperature effect. The transition state theory, we're going to take a look at this. When the molecules collide, and you saw this previously, reactant bonds are being broken and product bonds are being formed. And you can see this here, where This is a reactant bond. You can see it breaking here. This is going to be a product bond. You can see it forming here. This is an activated complex. It's a very high energy. It's very unstable. The point on the curve where this occurs is known as the transition state. So you can see the same reaction here. Here are your reactants. Here's their energy. The transition state is the point at the tippy top of the curve. Remember, activation energy is going to be from reactant to the tippy top. The point on the curve of highest energy marks the transition state. The activated complex is that transitory molecule. Transitory means it doesn't last long. Some people who are transient move in for a day and then they move out. See a lot of that down here. So here's the bond that's breaking. Here's the bond that's forming. This is the activated complex showing reactant breaking apart, product that's going to form. And then here are your products and here is their energy. And this too would be an exothermic reaction with energy of products being less than energy of reactants. And you do want to be comfortable with some basic reaction profiles. We're going to expand upon this. Not sure you saw this in middle school. I don't remember my daughter doing any of this, but maybe this year. For example, this would be a very simple reaction profile. Here's energy in kilojoules, and this will be your reaction pathway from left to right. We've looked already at exothermic reactions. So this would be exothermic, where you have reactant, R for reactant, P for product. Activation energy is the minimum amount of energy required for the reaction to occur. That's always from reactant to the tippy top. The point on the curve at the highest point is the transition state. We're going to get into that much more in a little bit. The activated complex would be the molecule as the reactant bonds break and the product bonds form. So this would be exo, and something like this would be endo, where the energy of the products is greater than that of the reactants. And again, EA is from reactant to the tippy top there, where you'd have your transition state. So endo versus exo. And that just shows reactant to product. We're going to get into this much more with the steps along the way.
In the exothermic one, delta H would be negative, and the endothermic, delta H would be positive, right?
Absolutely. And so if you did anything with this last year, you will recall, for example, that delta H is the difference in energy between product and reactant. You do product minus reactant, so delta H here is negative, and delta H here is positive. Endo versus exo. Exo, release of heat or energy. Endo, absorption of. Okay? And we're going to expand upon that in some detail. So activation energy is the minimum amount of energy required for the reaction to go. It essentially serves as a barrier between reactant and product. And a lot of what we just said is here. I apologize, I didn't plug those figures into your notes, but you do have them in your textbook. I can plug them in and repost it if it's helpful. The notes, it just gets to be a lot of pages, but if it's helpful to you, I can do that. So we mentioned the transition state, the activated complex, as well as the reaction profiles. The effect of temperature on reaction rate can be illustrated quite nicely here. It says an increase in temperature results in an increase in reaction rate for both endo and exothermic reactions. As the temperature increases, the velocity of the particles increases, and that's going to lead to more frequent collisions. And so now enough molecules are energetic enough to create a reaction. You're going to see a greater percentage of effective collisions, and you can see that here. And we talked about the Maxwell-Boltzmann distributions in the previous chapter, and you can see it here as well. Lower temperature, red is the higher temperature, warmer red. And what you're looking at right here is kinetic energy on the x and the fraction of collisions with a given kinetic energy on the y. And you can see a much greater fraction of collisions with a given kinetic energy such that it can overcome the activation energy at the higher temperature compared to the lower. So this whole area here is at the higher temperature. This smaller area here is at the lower temperature. So that's going to be proportional to the total fractions of collisions that have enough activation energy. And as a result, you're going to see at the higher temperature, there's a larger fraction of the collisions having sufficient energy for the reaction to occur. So at the higher temperature, the particles move faster and the percentage of effective collisions is greater. Hence, with an increase in temperature, you have an increase in reaction rate. You can calculate the effective temperature on K. You're not responsible for that, so we're certainly not going to get into that this year, something you might see in college. Our main focus today is going to be on reaction mechanisms. And when we talk about reaction mechanisms, we're going to expand upon these reaction profiles because we don't want to just see reactant to product. We want to look at every step along the way. So when the bell for second hour rang, you knew you had 6 minutes to get here. So your starting point was second hour and your finishing point was fourth hour. It doesn't matter if you went to the bathroom along the way, you saw your girlfriend in the hallway, you went to your locker, etc. in most cases. But when you're talking about reaction rate, it is very important what you did along the way. And so we're going to look at these steps along the way because they very much can influence whether products are generated. So in a reaction mechanism, we're going to look at a series of simple steps that ultimately lead from reactants to products. And this pathway is going to be critical. For a reaction mechanism to be plausible, the mechanism must account for the experimentally determined rate law. What you're going to see there is in a reaction mechanism, you have a series of steps. One of them will be slow. The slow step is the rate determining step. Think about it this way. Where do you want to go get a sandwich? What kind of sandwiches do you like? Huh? No, where do you want to go to get it? Subway, fine. You're going to Subway to get a sandwich. Now, one thing I absolutely want on my sandwich is tomatoes. And I look and there are no tomatoes in there. And that's unfortunate, and I want my tomatoes, so I'm going to get them. So now I have to wait for the girl to get the tomatoes, to wash them, to slice them, and to put them in the bin. Or you could go to Publix and probably get a better sandwich, I agree. But this is what you picked. So, that's the slow step right there. How long it takes her to get my yummy tomatoes, to wash them, slice them, and put them in the bin. Until she does all of that, can I have my sandwich? No. So that's the slow step. The slow step is the rate determining step. It determines the overall rate of the reaction because until that's done, nothing else can happen. So the slow step is the rate determining step. You can write rate laws from the slow step because they are rate determining. The other thing we're looking at is whether the mechanism is consistent with the stoichiometry of the overall net reaction. What that means in English is you want to be able to add up all of the steps so that all of the steps summed together equal the net reaction. Some of you may remember Hess's law from last year. It's going to look similar where you add up all the equations and it has to equal the net one at the bottom. And I'll show you how to do that. These series of steps, or each step, is an elementary reaction. It's a single stage in the progress of the overall reaction. So if I want to go from here to the door, but I'm going to do it in 3 segments, instead of just flying over the door, I'm going to walk here, and then I'm going to walk here, and then I'm going to walk here. And if I add all of that up, it'll equal to the total. So I'm going to look at those different steps, and whichever step took me the longest is the slow step, the rate determining step. When we consider slow steps, we want to look at reactants in these elementary steps. So molecularity is the number of species that must collide to produce the reaction indicated by that step. This sounds awful. It's wicked easy. A unimolecular reaction, what does uni mean? One. So a unicorn has 1 horn, a unicycle, 1 wheel. What else? Huh? Unibrow, 1 eyebrow. So this is a reaction that involves 1 molecule. So you're going to have 1 reactant only and a coefficient of 1. Unimolecular. First order. Bimolecular. Bi means 2. Like a bicycle. What else starts with bi? Bi what? Bilingual, biannual, etc. Biweekly. In this reaction, you're going to have 2 molecules colliding. You can have 2 of the same, and you typically wouldn't write A plus A, so you'd see 2A, or you can have A plus B. You're going to see second order there. I'll come back to that in a minute, but this is bimolecular. Ter means 3, like tertiary structure from, I don't know if you remember from biology, I'm not sure you learned it. In biology, we used to talk about primary and secondary structure with amino acid sequence, and then did you learn about like alpha helices? No. You don't do that anymore. You'd see that in AP Bio.
You got like tertiary consumers.
Tertiary, though, means 3rd, right? So ter is 3, or what other word would you have used? Tertiary consumers, that's a good one. Maybe not. So termolecular is when you have 3 molecules colliding simultaneously. Now this is less likely to occur. Think about the collision theory and tell me why a termolecular reaction is the least likely of those 3 to occur. Exactly. You'd have to have proper orientation of 3 molecules simultaneously. That would be tough. Think about those fidget spinners now when they're made. If they don't fit together properly, you're not spinning. You're not going to be able to drive yourself nuts with it. So in a termolecular, again, 1, 2, 3 in regard to coefficients. So termolecular, this is the slowest of the bunch because it would take the longest to position those molecules properly. Now, here's the key, and be very careful. When we talked about rate laws, we were writing rate laws from experimental data only, not from the coefficients in a balanced chemical reaction. However, you can write rate laws from the slow elementary step in a reaction mechanism. So exponents in a rate law for an elementary reaction only are the same as the stoichiometric coefficients in the chemical equation. So this is a little bit tricky. You can write rate laws from the slow step of an elementary reaction only. Be careful. The slowest elementary reaction is the rate determining step, and we talked about why this establishes the overall reaction rate. It's the slow step. It will have the largest activation energy of all the steps because it's the slowest one. It takes the longest to overcome that activation energy barrier. Now be careful. Sometimes they label the step as the slow step, but on the 2013 exam, they labeled it as the rate determining step, and half the nation didn't know what rate determining step meant. That is a synonymous term. I'll show you those questions at the end when we go through. All right. We are going to write rate laws from reaction mechanisms. The first set we're going to do is the absolute easiest set. This is when you have a slow step followed by one or more fast steps. When the slow step is first, you're like, woohoo, this is easy, and you let it rip. Let's take a look. It says a mechanism with a slow step followed by a fast step. We've got nitrogen dioxide reacting with carbon monoxide to generate nitrogen monoxide and carbon dioxide. We're given this rate law. What's the overall order? Second. When I did a plot and wanted to generate a straight line for an integrated rate law, what would be our y-axis? 1 over the concentration of nitrogen dioxide is correct. Remember, with second order, it's 1 over the concentration and your slope is positive. Okay? Be very careful there. If you plotted ln of the concentration versus time, you'd get a curved line. All right? Be very careful there. Here's a plausible mechanism. It says slow step, fast step. Now, sometimes it's written like this. Don't get upset if instead it said step 1 and then it was said slow step here. Or it could do this. So there's a lot of different ways that you can write these, and just be prepared for anything and everything. We are seeing some of this now, so if this is preferable to you, by all means, make sure you label it in your notes as such. It's all the same thing. I wouldn't sweat it too much. When you're looking to see if a mechanism is plausible, one of the first things you do is you add these two equations and you see if it equals your net equation. This is grossly similar to what you do in algebra. When you add two equations together, I have NO2 here, I have NO2 here, I have it here. That's similar to 2x on the left side and 1x on the right side, and you would simplify. So in this particular instance, I'm going to rewrite this on my paper so you can see the simplification process. This is step 1, step 2. You don't need to rewrite. You just need to watch and make sure you're comfortable with it. In step 2, I've got NO3 plus CO yields NO2 plus CO2. All right. So I have 2 of these and 1 of these. So I'm going to cancel 1, and this piece is going to drop down. First reactant. I have CO on the left and nowhere else. Second reactant. I see NO3 here and here. So those are going to cancel as well. A product in one elementary step showing as a reactant in a subsequent elementary step, it can be the next one or an elementary step after. A product in one elementary step, a reactant, the same reactant in a subsequent elementary step is going to cancel. That is called a reaction intermediate. That is your activated complex that doesn't last long. It's showing reactant bonds breaking, product bonds forming. And now I've got my other two substances, and these, I'm sorry, this doesn't have a 2 on it. NO here and CO2 there. So those are my two products. So I can see here that the sum of these two elementary steps is equal to the net equation that was given previously. That's the first criteria that must be met for a reaction mechanism to be plausible. It's the first thing you check. And if you're asked whether a reaction mechanism is plausible, it'll say list 2 criteria. That's one. The sum of these two is equal to the net equation. The way you write a rate law is you write a rate law from the slow step, because as we said numerous times, the slow step determines the rate of the reaction. So we're going to write the rate law from the slow step. The only time you use stoichiometric coefficients as exponents is from elementary steps, and you always start with the slow step. So this is my slow step here, and I'm going to write a rate law from my slow step. I write rate is equal to, this is my first step, so I'm going to write K1. 1 for the first step. I look at my reactants. I have 2 of the same. So instead of writing it like this, it more likely would have been shown like that. I wanted to show the easy cancellation. The coefficient of 2 becomes an exponent. You use the slow elementary step to write a potential rate law for your reaction. Now, for reasons I'm not going to get into, all the K's at the end just make K. And this is, in fact, the rate law they gave us. So the mechanism is plausible because the sum of the reactions is equal to the equation they gave us at the beginning, and the rate law is consistent with the slow step. It matches the rate law they gave us. If they didn't give us a rate law, you'd write it off the slow step and you would say that is the rate law. So again, a reaction intermediate is a product in one elementary step and a reactant in a subsequent elementary step. Rate laws are written from slow steps. If the slow step is first, it's as easy as this. No difficulty at all. Very straightforward. A molecular representation of this reaction is shown here, where you can see in the first step, the slow step, that these must be arranged such that you're going to nab an oxygen from here to plop right there, generating this reaction intermediate, and then that reaction intermediate will react with carbon monoxide And again, it's going to have to be positioned such that you can nab one of the oxygens and grab it onto here. A second example is shown here. A second example, oh, that's just not working. I won't touch it. A second example is shown here with the decomp of hydrogen peroxide to water and oxygen gas. Incidentally, last year in honors, you did learn that decomposition reactions are typically endothermic. It takes energy to bust things up. Synthesis typically exo. Not always, but usually. So what you're looking at here is a plausible mechanism. And again, slow step, then fast step. That's going to make it easy. And as I said, sometimes they write slow and fast on the right, and they indicate the steps on the left. Whatever floats your boat is fine. This is the same type of setup. What's the first thing you're going to check with this mechanism? The net equation. OI minus, why is that a reaction intermediate? Product in one elementary step, reactant in a subsequent. Now look at I minus. Iodide ion here is a catalyst. This is a reactant in one elementary step, and a product in a subsequent one doesn't appear in the overall reaction. So that's the reaction intermediate, that's the catalyst, and they're canceling two of these, one oxygen. So that's the first step. Now you're going to write your rate law from the slow step. So what you've got here is you're writing the rate law from here. Rate is equal to K1, concentration of the hydrogen iodide, concentration of the iodide ion, which is the catalyst. Now, typically you don't include catalysts in rate laws every once in a while, but you can just cancel that. The other thing I want to show you is the reaction profile that illustrates all of the steps. So what you're looking at here is energy on the left, reaction pathway on the x-axis here. Here is your reaction profile that illustrates the slow step and the fast step. What I do want to mention, I just grabbed this from somewhere, I'm not sure where, is I don't really like this Y thing. I was trying to cover it, but it's making a mess. If you looked at this profile, how could you tell from the profile alone that the first step is the slow step?
Because it has a higher activation.
Exactly. It has a higher activation energy. So from the profile, you would know the first step is slow. This is the second step. What's tricky here is the activation energy is always from reactant to tippy top. So this is really showing the activation energy in the reverse fashion. So here, I wish that arrow wasn't here. I can cover it, but every time I change the notes, the covering is going to disappear unless I link them together. So this is a little misleading. But what you can see here is the activation energy for the slow step from reactant to the tippy top. The top point is the transition state. The reaction intermediate would be right here. So you would put your reaction intermediate here of OI negative right there. All right, let's look at the harder ones. This is a little tricky. A lot of you are really zoning because you are so tired. This is the hardest part right here. So really try and focus. It's not that hard. It's a little mathy, but you're all stellar in math, so you'll be fine. Here it says a mechanism with a fast reversible step. Fast reversible means that the reaction goes forward and backward. The rate of the forward reaction is equal to the rate of the reverse reaction, followed by a slow. So here's an example showing the synthesis of nitrogen dioxide, likely to be exothermic, and they're telling you this is the rate law. We have a fast equilibrium step first and a slow step second. I've indicated K1, K negative 1, and K2. These are the Ks for the first reaction in the forward direction, the first reaction in the reverse direction, the second one only goes forward. First thing you do is check the net equation. What's the reaction intermediate in that reaction? N2O2. Product in one step, reactant in a subsequent one. Two of those, one of those, two of those. So the sum of those steps is equal to the net equation. First thing you want to check. You still write rate laws from slow steps. They are the rate determining steps as we talked about getting that sandwich. So the slow step determines the overall rate of the reaction. You're still going to write the rate law from the slow step. I'm going to illustrate this for you because it really can be tricky. I want you to see all the cancellation, the substitution, etc. Thank you. What you're looking at here is you've got, I'm going to rewrite this here. You've got, this is step 1, where you've got a bimolecular equilibrium reaction. How did I know it was bimolecular? Because you've got two of them. And then for step 2, is that uni or bi? Why is it bi? Because there's 2. All right. So we're still going to write the rate law from the slow step. Here's my slow step. I have rate. It's the second step. So K2, reactant, reactant. That's where I'm at right now. When I look at that rate law, when you look at that rate law, you can see that one of the substances is the reaction intermediate. So we really want to substitute that one. And we can substitute it writing a rate law from the fast equilibrium step and plugging it in. So I'm going to write a rate law from the fast equilibrium step both ways. I have rate is equal to K1 NO squared. And now backward. K negative 1 N2O2. Do you see what I did there? Forward and backward. What I want to substitute is the reaction intermediate, so I'm going to solve for this one. I'm going to divide both sides by K negative 1. Are you with me? Now I can substitute back in here. I'm going to put all of this right here. And I have rate is equal to, I've got K1, K2 over K negative 1, nitrogen monoxide squared, oxygen. For reasons that I'm not going to go into, this whole K caboose turns into K. And now the rate law that I derived is exactly what they gave me. So if you have a fast equilibrium step and then a slow step, write it from the slow step still, but it's probably going to involve some substitution. You know you'll have to substitute in if you have a reaction intermediate in your rate law, and you've got fast equilibrium followed by slow. And that's how you work it. It takes a little bit of practice, and you are going to get a ton today. Now, if you were diagramming this out, I've got a series of profiles to look at, but if you were going to diagram this out, what you're looking at is going to be, again, potential energy in kilojoules on the y-axis, reaction profile on the x. This reaction was synthesis, so it's likely to be exothermic, but more than likely they'll tell you. And we've got a fast equilibrium step followed by a slow step. So what I'm looking at here is probably a quickie step followed by a slow step, and we said this is exothermic. So the reaction profile would look something like that. If they ask you to label the activation energy of the slow step, again, you're going from reactant to tippy top of the higher curve. The other thing you want to be comfortable with is this is going to be transition state 1. This will be transition state 2. And right here is where you would have your reaction intermediate N2O2. And we're going to take a look at some of those curves to figure out number of transition state as well as reaction intermediate. And I'll show you an AP question where it was grossly similar. All right, so in your notes here, there's a whole bunch of reaction profiles. This is in a different textbook. I believe I did put some practice problems if you felt like you needed more, but I've typed out a whole reaction mechanism worksheet for you, and I think that'll do it for you, because very often the part 2 question will be something like this, and I'll give you an example in just a minute. So if you looked at this one, for example, is the first, second, or third step the slow step? Second, because it has the greatest activation energy. How many transition states? 1, 2, 3, and W and Y would be your reaction intermediates. Would this overall reaction be exo or endothermic? Exo is correct. Shown here is just reactant to product exothermic. In which of these two would the slow step be first? This one or this one? That one. All right. And here, if you had 3 steps, which of these 3 shows the slow step last? The last one. So you can read them. So the humps represent the transition state, and the intermediates are at the bottoms. Troughs. I was thinking the word troughs as opposed to crests. Shown here also is another one where you have 3 transition states, and there are your intermediates, also exothermic. We're going to answer this question together. I want to give you some time to work on it. I want to work through these problems with you. I do want to mention it is very rare that they have you propose a reaction mechanism. I did it in your lab, but we'll work on it together. I don't think that's likely. More than likely, you'll be asked to interpret it. I also just want to put the catalyst into perspective here. A catalyst, as we mentioned, is a substance that increases reaction rate but is not altered at all. Now, a lot of people will just say, oh, the catalyst lowers the reaction rate. The catalyst lowers the activation energy, but that is not what it does. Be careful there. Whenever you've seen profiles of catalysts, you've probably seen it like that, where here's the uncatalyzed pathway, here's the catalyzed pathway. What a catalyst actually does is it provides an alternative pathway, a different mechanism that has a lower activation energy. And now more molecules will have enough energy to engage in effective collisions. So a catalyst is a substance that's not altered. It increases reaction rate because it provides an alternative pathway with a lower activation energy. For example, if you look at the decomp of potassium chlorate, if you add manganese 4 oxide, that is a catalyst that increases reaction rate. If you compare these two profiles, you've got the number of collisions with a given energy on the Y. You're looking at energy on the X. In an uncatalyzed reaction, only these collisions here will have enough energy to overcome the activation energy barrier. In contrast with a catalyzed reaction, many more collisions with enough energy to overcome the activation energy exist. So a catalyst is a substance that increases reaction rate by providing an alternative pathway that has a lower activation energy. Your book gets into homo versus heterogeneous catalysts. Honestly, with homogeneous catalysts, the catalyst is in the same state, let's say gas, as all the reactants and products. In a heterogeneous one, it's in a different state. Not that concerned there. Enzymes you would have learned about in biology. An enzyme is a biological catalyst, typically a protein that increases the rate of a biological type reaction. For example, carbonic anhydrase is an enzyme that increases the rate of the reaction to make carbonic acid from carbon dioxide and water. For those of you interested in biochem, you'll do a lot with enzyme substrate complexes. Enzymes typically configure reactants such that they can be positioned correctly. And for those of you who are interested in your textbook, this is a good read. We are going to take a break in a minute. When we come back from the break, you'll work on this problem. We'll look at these AP problems together. I think that will be extremely helpful to you. And then you'll work on your classwork. Your goal today is to be able to write rate laws from reaction mechanisms. With practice, you will be very successful with it, and it all kicks back into the original learning goal, and this is big idea 4. You want to be able to illustrate that reactions have rates that are very much determined by their molecular collisions. And if you understand reaction mechanisms and how to write rate laws from them, you'll be very successful. Also, we'll reiterate the importance of what we talked about at the very beginning. In order for a reaction to occur, the particles must hit each other with enough energy to overcome the activation energy barrier, and the molecules must be oriented properly. That will be critical, and we will work on this problem in your notes together, as well as several problems from some previous AP exams, and that should give you some confidence with your kinetics chapter. Kinetics is very easy. It's the easiest quiz you're going to see of the quarter. All right, I'm going to postpone it till Monday simply because so many kids are out sick. All right, so we'll take a break and then we'll do this.